I know many of us probably already know Calcul Québec. Maybe you're already using it. We saw our logo on many of the posters. But for those of you who may not know us, I'll just go through a few slides before I hand it over to Denis and Denise to talk to you about quantum computing. So that's what we're going to talk about today. Just Calcul Québec in general, what are the services we can offer to you, and then more about our upcoming quantum computer. So these are all the universities that are members of Calcul Québec. If you know the university landscape in the province, that's 15 out of 18 universities. So there's 3 more that we need to catch up with. That was supposed to be our goal for this year in terms of membership. And we're part of the Digital Research Alliance of Canada. So we're collaborating with researchers, with colleagues across the country, and we're working for researchers across the country as well. This is our mission statement. So our goal is to provide modern computing systems. This is why we're going to work with quantum computers as well. And on top of providing users with servers, high performance computing servers, we also provide the expertise to help users use them appropriately. And we provide training. So we'll see all of that in a little bit more details. And that's where we really have added value is all the support that goes with the hardware. A few numbers. So these are numbers from 2021, so they're already a little bit old. I need to update this slide. But you can only imagine like more than 4,000 users are using the service in more than 1,000 different research groups. I can maybe already go here. Here we're going to see how the number of users, depending on the research domain, evolves with time. So on the left, what you said, I don't know if you can read very well, but you know, the 4 series of numbers on the left, these are for applied and pure sciences. This is kind of the traditional community of HPC users. And you can see there's growth, but it's kind of regular over time. What you're seeing is the numbers from 2010, 2016, and 2022. If you're looking here at the numbers in the middle, that's mathematics and computing science. This is AI. So you can see that 12 years ago, there were like 47 users. And now we're close to 1,000 single different users. These are actually people launching jobs on the systems. So they're really active users. If you just have an account, but you're not using the system, you're not in this graphic. So it's really active users. Another interesting one here is the community of health sciences, biology, things like that. That's the genomics community. If you remember, if you're old enough, in 2003 was the first, when the genome project, the Human Genome Project ended, that's the first genome that was decoded. At that time, that was done on a laptop. Because a human genome, I mean, it's not that big. And if you're just doing one, you can do that on the laptop. And then what you need to know is that the technology of sequencers, that's rapidly evolving. Every 9 months, the capacity of a decoder is doubling and the cost is divided by 2. So that means that every year, the capacity of analysis by the community that's really an exponential growth. That's much faster than the growth of the computing power. And so what happened around 2010, 2012 is that computations could no longer be done on a laptop. And then that's when the community arrived and started using supercomputers. And you can see there as well, you know, going between 2010 and 2022, that's a large increase in number of users. that community is now the community who's using the largest amount of storage on our systems. The only group of people that can compete in terms of the amount of storage, that's the huge telescope projects, things like Kind in the West, or the square kilometer array that's coming, things like that. Otherwise, that's the community that's using the more data. And then here on the right-hand side, we've got new communities who are starting to use our systems, people in humanities, social science, psychology, people doing text analysis. This is really emerging. And this is where there's a lot of work for us to do, because we need to get these people to start using our systems. And they're not necessarily well trained in using command line systems. If I go back in time, it's just to show the growth of our user community over the last 12 years. You can see that's kind of a straight line, you know, ups and down, but it's still growing. So I think we have work for many more years. If ever you're interested to come and work with us, I think this is this shows that there's going to be job for you in the future. Our services, for those who don't know what we're doing, first thing, we're dealing with the supercomputers. We're buying them, installing them. We're doing big national systems, but we also do that for research group. If you have a CFI grant to procure a few servers, and you don't want your master student to spend his or her time, you know, working with that system, you can hand it over to us. We manage it for you, and you can use it anytime. And so that's the first part. Second part on the right, we're helping us users use the systems efficiently. So you can talk to an analyst to try to understand what your needs are, how to do things better, maybe how to use storage better, how to get rid of temporary data that is not useful. If you're not doing that, please do that. How to configure software, how to optimize workflows, how to combine applications together to be more efficient, how to visualize things. And of course, we write a lot of documentation that's available in both French and English. So that's probably one of the rare places where you can find good French documentation. So you should really take advantage of that. And then we have our training program. We have training over the course of the year, but also, and I'm going to skip a few slides here. I want to advertise our summer school. Well, it's actually a spring school because it's in May. So it's 4 days. In-person training. And so what's really nice about that is that you get to spend a lot of time with our specialists. And so like in the evening after the class, you can talk about your own private problem. So that can provide more insight into what you're actually working on. It's really cheap. It's like $400. That includes food and lodging. So that's the only thing that's costing you. So it's really cheap, 4 days, really worth it. I really encourage you to attend if you're doing HPC. A few links that's going to be in the slides that you're going to receive afterwards. That's not useful. And what are our current infrastructure for those that are using them? So we have the big HPC systems, Narval and Beluga. 130,000 computing cores, 1,500 GPUs overall available to the community. We've got our team takes care of installing all software centrally, so you can have so it's really transparent for the user. You can just use it. You can also export the software stack on your own PC and have the same software environment locally than you have on our big systems. That's also very useful. We also have virtual machines that you can configure depending on specific needs you may have. You can do interactive computing through notebooks, and we have, of course, a huge amount of storage available. That's already available, and coming soon, the quantum computer that's our data center. And that's our future quantum computer. And I will leave it up to Denis to talk to you about the hardware.
Yeah. Okay, so good afternoon. So before Denise goes in her deep dive analysis of quantum computing, we're going to talk a bit of hardware. I presume engineer would be interested. So, no, this way. Okay, before we go into the machine, just to explain how it's built. Basically, it will be connected to Narval, but that's where you prepare your program. For Alien, it's in Julia, and you submit your program to our scheduler, which is Slurm. And this program will talk to a classical computer inside the Monarch computer, which control the microwave, which sends the microwave instruction to the chip into the cryostat on the left. But this is how it's architecture. So this is in yellow, it's simply our network. Standard, it's in the room, and we send the instruction this way. So from a general architecture, that's how it is. If you go inside the machine, so what you have on the picture on the left part, that's the cryostat without the canister. That's the chip is at the bottom of it, and that's where you get like 40 millikelvin temperature. And as you go higher, say it's a bit warmer. The big pipe on the top is where the helium goes back to the cryogenic. It's the compressor that's on the right, and goes back with a smaller pipe. You will also see that's when it's cooled. So big pipe going back a small pipe. What else? It's a mixture of helium-4 and helium-3. It's just at the frontier of helium-3 when it dissolves to helium-4. That's where it's the coolest, but that's where it resides. And it's the helium-3 that's recirculating. So on the right, that's the canister when it's closed. Well, this picture were taken this week. That's how advanced it is. It's an Indian site right now in Dorval, far from here. The plan is to have this autumn. We have well, for those on IT, you probably know it's kind of difficult to have some parts these days. We have the same problem. So for the electronic part, that's the issue. So we got a bit late on their schedule. So sometime in October, it will be available. If ever we get the budget for 24 qubits, so that's a 12 right now. If we go for 24, then we'll leave it there, connect remotely until they disassemble, change the chip, reassemble, and then finally send to us at ATS. So that's how it is. Power consumption, what we have, it's about 35 kilowatts, so kind of a standard rack. It's like, maybe you don't see, the cube is 11 feet by 11 feet by 11 feet. So you can say it's about 4 racks, but put together. It has a consumption of about 1 rack. And the cooling is the standard cooling we have for our room. So it's all water coming at 15 degrees and exiting at 25. What else? The electricity, it's 100 amps going to a UPS. So they have their own UPS. They are not on our UPS. And then which feeds the machine. Oops. that's it. So that's basically the hardware part of it. Thank you. See.
Okay, so Monarch is our quantum computer that's going to be coming in well, at the end of this year or earlier next year. But in the meantime, we do have accessible on our current Beluga and Narval a simulator quantum computer that uses Julia as a programming language and a library of commands that's called Snowflake. So if you're interested in quantum circuits, you can already start playing around with the quantum simulator that is called Snowflake. Why I'm mentioning this now is just I don't have that on my slides. So Snowflake, which is from the company Anion, it's available on GitHub, and you can use it either on our computers or you can also use it at home as long as you install Julia. Okay, so why are we interested in quantum computers right now? Well, just in September last year, Jensen Huang, who's co-founder and CEO of NVIDIA, said that Moore's law is dead. Well, what is Moore's law? It's the number of transistors that you can fit in a processor, says that that number will double every 2 years. We have hit the point where transistors are at an atomic level. In other words, we cannot go smaller unless we go into the subatomic domain. Okay, and that's one of the interests with using quantum computers now, is that quantum computers uses the subatomic domain, and so deals with, instead of using the laws of classical binary mathematics, uses the laws of quantum mechanics. Okay, so how many of you here, I suppose you have a little bit of knowledge of quantum mechanics here? What is a quantum particle relative to a normal particle? Is that it has dual properties. It is both a particle and a wave. Okay, and what quantum mechanics is basically is a mathematical formulation in order to be able to predict the properties of both these particles and wave at the same time. There are many mathematical formulations for quantum mechanics, but the one that is most known is, of course, the Schrödinger equation. Okay, so the Schrödinger equation is a linear partial differential equation. As engineers, you know these equations very, very well. All right, so that's why I decided to start with the Schrödinger equation, because it's a mathematical language that you are accustomed to in your classes. So what the Schrödinger equation consists of is here a partial differential equation over space and time of a given function that we call psi. Psi is called the wave function, so it describes all of the physics or all of the behavior of a quantum particle. So all the information you need to know about your particle is contained within that wave function, which is called psi. Okay. So the other particularity of quantum particles is that rather than existing in a continuum of states, so if we say speed, for example, is a continuum of different states, for a quantum particle, they exist in discrete energy levels. So a particle can be at a given level of energy 0, for example, and then at a level of energy 1 or 2 or 3, but cannot be at 1.5, 1.2. It has discrete energy levels. So in order to represent that, we decompose the wave function into what we call a linear combination of states, energy states. So here, I don't have a pointer, but we can see it here. So a linear combination of states which represents each of the states, energy states that a particle can take. With here a certain, the C of I here is a certain amplitude of, or the importance of that state within the particle, if you will. So this is what we use, this linear combination of states, in order to describe these states of our qubits, okay? So if we look at a qubit as a quantum particle, okay, which it is, all right, there are within quantum computers, a qubit can be an electron. As in the case of Monarch, it can be a superconductor. I'll be talking about that a bit more in a minute. It can be an atom. Okay, there are various ways, to emulate quantum particles. Okay, they're quantum. So a qubit has two distinct states. Okay, 0 and 1, just like a classical bit in a computer. It's either a classical bit, it's either 0 or 1, on or off. A qubit also had those two states. If you know an electron has two spins, either up or down. Okay, these two states correspond to the spin states of the electron, either up or down. However, the qubit can also be in a superposition of those states. Okay, and this is where we have these coefficients here, alpha and beta, which are the percentage of how much the qubit is in either one of these states. So on top of having the two states, 0 and 1, as a classical computer bit, it can also take on all possible values of 0 and 1 with given percentage. So this is where we see that we have the particle wave duality. Okay, so the states 0 and 1 are the discrete energy levels, but the alpha and beta are continuous. Okay, so in this equation here, we have both a continuous state, okay, which is the properties, if you will, of classical particles. So it's continuous, but we have the discrete energy levels 0 and 1. Okay, so in this way, we describe both a continuous and a discrete particle. All right, so as said, the qubit can be represented, if you will, in the Schrodinger equation as the wave function. And here we have this H hat. H hat is called the Hamiltonian. I don't know if you're, if you have a lot of knowledge about Hamiltonians. In the case of quantum mechanics, the Hamiltonian represents the kinetic and the potential energy of a particle. And we express that in terms of an operator. So let's say we have the equation for the kinetic energy of the particle, and we have equations that represent the potential energies of the particle. We apply that to the wave function in order to find exactly in what probability the particle is in. So in this way, the Hamiltonian, when we bring that back to a quantum computer, we are not exactly describing the states of the particle per se. That's not our interest. We are interested in doing operations on that wave function or on that qubit, and those operations that we are doing can be seen as this Hamiltonian operator. So in the case of quantum computing, we use what are called unitary transformations. Okay, so they are basically operations that we do on the qubit. Okay, and so the solutions that we obtain from a quantum computer are probabilities. A probability that a particle will be in a given state. Okay, so what we obtain from the quantum computer is basically these amplitudes, the C of I's, and these correspond to the solutions to our wave function. Okay, but as soon as we measure, all right, a qubit or a quantum particle, we have what is called the collapse of the wave function. All right. So what happens is that the wave or the particle exists in all possible states at the same time before we measure it. But as soon as we measure that particle, it will collapse to either the 0 or the 1 state with a given probability alpha or beta. Okay, and that's what we can obtain from the quantum computer. Okay. All right. So as I said, the Hamiltonian operator, we can translate that onto a quantum computer into operations that we do on the quantum computer, which we call quantum logic gates. Okay. So they are similar to logic gates that are done on a classical computer. We have the AND, the OR, the NAND, the NOR. Well, in terms of the quantum computer, the gates are actually ways to change the phase of our qubit. Okay, so rather than saying one bit and another bit, what we're doing is we're changing the phase of our qubit, okay, with the logic gates. All right. So here, a classical bit, as I said before, is either 0 or 1, whereas a qubit can take 0 and 1 and can be in a superposition of both of those states at the same time. So it's both in the 0 and 1 state at the same time, which gives a lot of parallelism to the qubits rather than relative to classical bits. All right, so a qubit, okay, if we take 2 qubits, all right, or more qubits, if we look here, a classical bit, if the number, depending on the number of bits that you're using, you can have 2 to the n combination, 2 times n combinations of classical bits. Whereas for qubits, we have 2 to the power of n possible combinations of qubits. Okay, so here we have an exponential increase in the amount of information that a qubit can deal with relative to a classical bit. So here, before going into too many details about the gates, I'm not going to go into details about the gates here, but you have 1 qubit logic gates, 2 qubit gates, and 3 qubit gates. The power of quantum computing is when you are able to work with more 2, 3, 4, 5, 6 qubits, that you are able to superimpose many qubit states, so that you can act on more possibilities of your system at the same time. So here the gates, the 1, 2, and 3 qubit states, you can use those in order to look at superpositions of a larger number of qubits. So with these basic logical gates, you can actually deal with a large number of qubits. Okay, just as in classical computing, you can use these simple logic gates in order to create much more complex problems. Similarly, for qubits, you use these very simple, basic gates in order to create more complex logical algorithms. Okay. So what is the quantum advantage? Okay, that's something that people talk about a lot. What is the advantage of a quantum computer over a classical computer? Well, its main advantage, as I said, is the capacity to be able to deal with a large number of states at the same time, rather than looking at each state, binary state individually, like a classical computer will do. Okay, so a classical computer will look at its bits one at a time, whereas a quantum computer can look at a full set states at the same time. Okay, so some of the algorithms that show quantum advantage are faster on a quantum computer than on a classical computer are the algorithm of Shor and the algorithm of Grover. These are two examples. There are many, actually. So the algorithm of Shor is one that factorizes prime numbers. So basically, it's the algorithm that permits to break our current RSA encryption, which is based on the factorization of prime numbers. As we can see here, for a classical computer with the current state of RSA, which is 4,000 and something bits at the time or more, it can take 1 million years for a classical computer in order to break that encryption. Whereas a quantum computer with a sufficient number of qubits could actually break or find the prime numbers within a few seconds with the Shor algorithm. Okay, however, it takes quantum computers that have enough number of qubits in order to do that. And for now, the largest quantum computer of the universal type is 477 qubits, which is not yet large enough to break our current encryption. However, that is coming. So very soon, our quantum computers will be able to break our current encryption systems. And one of the areas of development in the field of quantum computing is quantum cryptography. We'll come into that in a minute. Another field where quantum computing is very strong is in terms of searching unsorted data. Okay, with the algorithm, the Grover algorithm. For a classical computer, in order to search an unsorted database, it needs to look at each one of those entries one by one. Okay, the Grover algorithm allows to look at a large portion of that database at the same time and be able to find what the data of interest in a much shorter time. So quadratically smaller time than with the classical computer. Another algorithm that I don't show here is called the HHL algorithm. So it's Harrow, Hasidim, and Lloyd. And that is an algorithm that is faster on quantum computers than on classical computers to solve linear equations or systems of linear equations. So this is something that is more of interest to you, I believe, is that yes, with this HHL algorithm, you're able to solve systems of linear equations much faster on a quantum computer than on a classical. So the other difference between a classical and a quantum computer is the fact that a classical computer will always yield one result. Okay, a quantum computer yields probabilities. All right, so you will get a larger number, you will get more results with probabilities of obtaining that result. So if you're looking, for example, at what is the fastest way or the fastest route to transport a number or to deliver a number of packages to people in a city, there can be many solutions to those linear equations that you use. There can be many solutions to that. The quantum computer will show all possible solutions with a higher probability for the solution, which is the best. However, it allows you to see all possible good solutions. And after that, you say, okay, this is maybe the best, so the one that's the most probable. But look at those on the other, there's other solutions as well and maybe preferable. So the quantum computer allows you to have many solutions, and therefore you have a choice, if you will, in terms of what solution you will be using, rather than having just one solution. Okay, so now we're coming back to Monarch, our quantum computer. So Monarch is what is called a universal quantum computer relative to a quantum annealer type computer, which is specialized in optimization problems, one of the great forces of quantum computing, or analog computers, which use molecules to emulate certain types of functions. Very briefly. So a universal quantum computer can, if you will, do optimization problems as well as look at molecules. And so we call it universal because you can look at, you can treat many types of problems. All right, so in our case, the qubits are superconductors. Okay, a superconductor, this is where we have the cryogenic system here. Superconducting materials or metals exist in the regime close to 0 Kelvin. All right, at 0 Kelvin or close to 0 Kelvin, the electrons within the free electrons within a metal that normally, you know, we use for electrical current, etc., become, rather than being repulsive, they become slightly attractive and create what are called Cooper pairs. These Cooper pairs flow freely without resistance, okay? And that's why we call them superconducting. They have absolutely 0 resistance, okay? However, the energy levels, all right, so here we see here a little bit a schematic view of a superconducting qubit. So here the U represents the electrical current. The dotted line here is the portion that is superconducting. So we have an electrical current. We pass it through a very, very cold environment. The electrons become superconducting. Okay, and we have a capacitor to hold those electrons. And here we have the E of J, which is called a Josephson junction. That Josephson junction is a very thin layer of an insulator, okay, which basically breaks the flow of those electrons and allows to create 2 distinct states, 0 and 1, okay? And the electrons can tunnel through that insulator level with a predictable tunneling effect. So we can predict how many electrons will pass, and we can tune the Josephson junction to have energy levels that are closer together or further apart. Okay, so it's the Josephson junction that creates the 2 states of our superconducting electron Cooper pairs through the effect of tunneling that quantum particles have. I did not touch it.
Oh, good.
I didn't even touch
That's
the
the
arrow.
quantum computer that is booting. Je pense,
It just went
je pense que c'est la lampe qui vient de mourir à mon avis. Ouais, alors, tu peux aller voir, mais à mon avis, c'est foutu. Hein.
Bon.
Est-ce qu'il y avait plusieurs autres slides? On peut les décrire.
Ouais,
Je suis déjà allé dans une conférence, okay, où il y a eu une coupure, c'était en Californie, à San Diego, il y a eu une coupure électrique pendant 3 heures, et les gens traçaient leurs slides sur des flipboards. Mon graphique, c'était ça.
Ouais. Bon, ben, il me restait.
Désolé, la lampe vient de mourir.
OK. I was just
Oui, pardon.
conducting the connectivity.
Oui, ok.
Yeah. It will give you 3.1, it will give you various different answers, with probably the most probable being 3. However, you will not it won't be 100%. No, you will not get that. And so quantum computers are not good for banking. You can't use it as a calculator. It's really used for difficult mathematical problems that are very difficult to solve on a classical computer.
So what should we do? Should we continue without the slides?
Yeah, I'll try to continue without the slides. The next slide was to show actually the quantum processor unit of Monarch. It's a 12 qubit computer, and the way that it looks a little bit like a Monarch butterfly. So that's the reason why we called the computer Monarch. And the important thing with superconducting, the important aspect of quantum computing is being able to superimpose and create entanglement between the different qubits. In a superconducting computer, you can only do that with the nearest neighbors. So at most, one qubit can be connected to 4 other qubits. Okay, and so with the diagram of that connectivity. So when you're writing a quantum circuit, you need to take into account which qubit you're actually talking to. So when you're programming a quantum computer, it's like going back 60, 70 years now and using machine language. You are talking directly to the mechanical components of the quantum computer. So in a superconducting computer, the different states, okay, or the phases or the superposition state are controlled with microwaves, okay. So we control the microwave to have it change the state of the qubits, okay. The logic gates are various ways of changing the microwaves in order to change the state of the qubits. So the important thing here is that in superconducting quantum computers, when you're writing your circuit, you need to take into account your nearest neighbors in terms of the qubits and where they are within the quantum processor. And I think yes, the other important point is you have the gate time. So the gate time is how long it takes for the microwave to reach the qubit. That's very, very, very fast. That's in nanoseconds. However, the time that a qubit can stay in a given state is microseconds. Okay, that's called the coherence time. So a quantum computer cannot store information. The information that it holds, it can only hold for a microsecond or less. Okay, so that's why you always need a classical computer, okay, hooked up to your quantum computer in order to store the information that the quantum computer cannot. And you also cannot make logical circuits that are very, very long because your circuit needs to be on the time scale of the coherence time. The qubits, or how long it's able to keep its given state. And so I wanted to go into some of the applications. Okay, for you as engineers, one of the main areas of development right now is actually optimization problems, solving linear equations. We are now into solving nonlinear systems of equations. Partial differential equations. It's one of the main strengths of quantum computing and in very, very active development at the moment. Another one of the fields that is coming up is the simulation of chemical systems, pharmaceutical systems, materials, okay, because qubits are inherent to the materials. Okay, there are electrons in molecules. That's what we try to simulate very often, and we can simulate those directly on the quantum computer without going through all of the complicated mathematical formulation of solving the Schrodinger equation. Okay, so that's one area where quantum computing is very, very strong. Artificial machine learning, artificial intelligence. Okay, we know that a neural network is only as good as the number of neurons that are, I may be simplifying this. But a lot of the neural networks will depend on the number of neurons you have. So with a quantum computer, you can treat a large number of neurons at the same time, and it's much faster. Oh, came back.
Merci.
Okay. And finally, a very, very important, I did not go into this at all, but one of the important properties of quantum particles is that they can become entangled. What that means is that if you have two bits, you can entangle them to be in absolutely the same state at the same time. And if you take those two qubits and you push them apart, no matter how far, Einstein called that spooky action at a distance. You can teleport the qubit to thousands of kilometers away, and it will still be in the same state as the original qubit. Okay, and if you measure one qubit, the other qubit will flip over. So if you have spin up on this side, it will be spin down on that side, and you will know exactly what we're supposed to be having with the second qubit on the other side. So now the whole problem, we are able to entangle qubits very easily. However, it's transporting those qubits over long distances. So now we, very recently, China has been able to transport two entangled qubits over around 100 kilometers. But the hope is that we'll be able to do much longer distance transportation in the next upcoming 20 years in order to allow full global quantum network. Okay. And any questions?
So you do the bachelor's degree?